Okay, next is a part 2 of our I/O system chapter. So in this section, we'll discuss about the structuring techniques and interfaces for the OS that enable the I/O devices to be treated in a standard, uniform way from the system perspective. So for instance, for example, how an application can open a file on a disk without knowing what kind of disk it is, and how new disks and other devices can be added to a computer without disruption of the operating system. You have an experience, right? When you want to access the file, you didn't care what type of device, as long as the disk or the storage attached to your system, you can view, you can click. So if you add on new external disk or flash drive, your system still there, not corrupt, right? So without disruption. This is the main concern of I/O management. And then each of these I/O actually access to a standardized set of function. They call it interface. So all your I/O having your own interface using the port. So the different are the encapsulated in kernel module, which we call it as device driver, that internally are custom tailored to specific device, but they export one of the standard interface. Okay, the purpose of this device driver is actually to hide uh, the difference among the device controller from the I/O subsystem of the kernel, so that the kernel only see the standard interface or standard form of connectivity. So the I/O system call encapsulate the behavior of device in a few generic classes that will hide the hardware difference from the application. So this practice will make the I/O subsystem independent of the hardware. So any hardware that will track the same thing or same mechanism, and can simplify the OS developer if they need a different uh, mechanism to connect with the system, so that your OS developer will having a lot of issue in design and developing your OS. However, unfortunately, the device hardware, although you have same device like GPU, however, each OS has its own I/O subsystem structure and device driver framework. So the developer of the device driver need to specifically write the device driver for each operating system that can support their hardware. So what are the difference actually from each OS from another OS? Most of the time, the device will be buried in this dimension. First, about character stream or block. With character stream, device transfer byte one by one, whereas a block device transfer block of byte as unit. There are some OS using stream, some OS using block base. Okay, and then different in terms of access, either using sequential access or random access. Normally, sequential access device will transfer data in a fixed order determined by the device, byte by byte, right? And then using all the flaws, and so on. Whereas the user of random access device can instruct the device to seek to any of the available data storage location that they required. This means using the address block. Yes. Okay. And the third different actually normally either the device can be accessed synchronous or in asynchronous mode. Normally for synchronous device will perform data transfer with predictable response time. Okay, make it synchronized in coordination with other aspects of the system. But for asynchronous device exhibit regular or unpredictable response time, which not coordinate with other computer event. Now the difference actually based on shareable or dedicated. Shareable means the device can be used concurrently by several process or thread, but the dedicated device cannot, only one by one. Another difference actually about the speed of operation, because some speed have a range of few byte per second, and then some speed have a few gigabyte per second, depend on the requirement of the device itself. Read only or write only, another different. Some device perform both input and output, but others support only one data transfer direction. This is the difference between the device I/O and their interface. Okay, this figure represent or illustrate how the I/O related portion of the kernel and structured in software layer. So you see the kernel itself in the upper level with the kernel I/O subsystem. They have the device driver and hardware. You see, SCSI device controller will connect to SCSI device. SCSI normally will used by the this storage interface, keyboard controller, mouse controller, PCI buttons, and others. So you see the device driver will translate, you can call it as translate all the instruction into this uniform kernel I/O subsystem, so that your kernel only see the same standard of kernel I/O subsystem, although they are connected to different hardware. And then this figure represent the example of characteristic of I/O devices. There are aspects that we can differentiate them in terms of data transfer mode, access method, transfer schedule, sharing or dedicated, right? So from the previous slide, we can see example. If in data transfer mode, for example, character or stream, example is terminal. In terminal, when you write the command, they will send the data using character by character or string. But for the block, normally in this level, when we copy or we could paste the file from the disk into another disk, for example, you are using block data transfer mode. For access method, modem normally will use sequential, one by one, step byte by byte, right? But for random, like CD-ROM, you can directly go to specific address space. For example, you want to access one song from that CD, they will directly go to that song. They don't go through from the starting of the disk address. This is random. That's why you see ROM, random access memory. Compact disk, random access memory. For the transfer schedule, synchronous or asynchronous, like synchronous tape, dedicated for sharing or shareable, tape dedicated, shareable a keyboard, right? And device speed, need to concern about latency, seek time, and many more. Other than that, we have a character of I/O device that we can differentiate. Normally, the subtleties of the device will be handled by the device driver, which broadly I/O device can group into the OS by the OS into either block input output, character input output, memory map, file access or random, or network socket, and so on. So we can see one by one later based on this characteristic. For direct manipulation of I/O device specific characters, usually an escape or backdoor, you can use this function. Like in Unix, they got IOCTL call to send arbitrary bit to the device control register and data to device data register. This look like the shortcut. Okay. So the first character is about the blocks and character devices. Either they transfer in block format or character format. So the block device interface capture all the aspects necessary for accessing this drive, and other block-oriented devices. The device is expected to understand commands such as read and write. If it is a random device, it's also expected to have seek command. That's mean to seek the specific address of the data or block of the data to be transferred. Okay. There are also some special application such as database management system which prefer to access block device as their simple linear array of block. So this type or this mode of access, sometimes we call it as raw I/O. We have also direct I/O, which actually based on Linux or Unix mode of operation, which allow the OS to be accessed in block. Other than that, the memory map file access also can be layered on top of the block device driver. In this approach, normally file will be mapped to virtual memory and clustered block via the demand paging technique. Also for block device, we can use DMA, direct memory access, to access the device. For character device, like the keyboard, mouse, or serial port, it will be support character stream interface. So the basic system call in this interface will enable an application to run the get or put function on character. On top of this interface, libraries can be built that offer line at time access with buffering and editing services. For example, here when you press the keyboard, right, like you press backspace, and then the preceding character is removed. The previous character is a character by character. If you press longer, maybe 3 or 4 character, previous character will be removed. Another common interface or I/O devices, actually network device lah. We have Bluetooth, Ethernet, right? Wireless Ethernet, and many more. Varying enough from block and character to have own interface. So normally you can connect your network device using PCIe for PC, but for laptop they integrate together in your mainboard. Sometimes you can connect using USB as well. For logical layer or device driver, normally they name it as a socket interface lah. Linux, Unix, Windows include the socket interface. You can assume it's look like your socket for electricity. Any electrical appliance can be plugged in. By analogy, the system call in the socket interface enable an application to create their own socket, then to connect a local socket to a remote address, and to listen for any remote application to plug into the local socket. So each of the network application, they will use different socket. So you can separate network protocol from network operation. They have the include function, include the select function. Okay, select functionality. Normally this select function will support the implementation of socket. Then manage a set of socket by this function as well. So this select return information about which socket have a packet waiting to be received and which socket have room to accept a packet to be sent. This is the select function in the network device. There are variety or widely approaches can be used in managing the network device with the inter-process communication and network communication, like the pipes, first in first out stream, queues, and mailbox. Other I/O is a clock and timer, which will provide computer with the current time elapsed times, or a timer that you can set to trigger any operation in the operating system. Okay, normally the resolution about 1 per 60 second, 1 second lah. Okay, some subsystem or some system provide higher resolution timers. It depend on their requirement and their standard they follow. Example of the timer device actually, the hardware is a programmable interval time which can be used to measure elapsed times and to trigger operation. Okay, this is the thing. Also used for timing or any predict interrupt. So I/O control function normally in Unix actually cover this aspect of I/O, such as clock and timer. They got also in networking, they got NTP and many more. This is a clock and timer devices, or we can call it as the function. Next, we look at the non-blocking and asynchronous I/O. Blocking means the process suspended until I/O completed. They can block the resource before the I/O complete. Easy to use and understand. However, insufficient for some needs, because if they block, other process need to wait. Right? If let's say the process, the I/O usage are very long, then there are many process required to be waiting. And then non-blocking, normally I/O call return as much as available. It is available, they just offer to use. Normally for user interface, like the data copy, can be implemented using multi-threading system. This will be written quickly with count of byte read or written. You can use a select function to find if data ready, then read or write to transfer. The non-blocking is not exclusively for specific process, right? Other technique in operating system, you can use asynchronous, which the process run while I/O still execute. Difficult to use, but they have some mechanism to make it happen. Normally, there's I/O subsystem signal process when the I/O completed. This is example of how these two I/O methods, synchronous and asynchronous, work. In synchronous, you need to go through one by one. Right? Requesting, process waiting, device driver go to the interrupt handler, and then hardware data transfer go through back to the cycle request process after complete. After complete, they can go back to request process. But for asynchronous, although the process is still in the progress or execution, the hardware data transfer still can transfer the data in this without required to waiting for the current task complete. Other than that, some OS provide another major variation of I/O using the application interface, like the vector I/O, which allow one system call to perform multiple I/O operation, which involve multiple location as well. For example, here the unique read VE function or system call accept a vector uh, of multiple buffer and either read from a source to the vector or write from the vector to a destination. And the same transfer could be used by several individual invocation of system call, but this gather method is useful for a variety of reasons. Especially it can be better than multiple individual I/O call itself, because one call can use a multiple operation. So this approach or technique can decrease context switching and system call overhead, so the CPU usage will be optimized, will be lower, or will be acceptable. So in another layer, we have kernel IO subsystem after your device driver layer, right? Then you will go to kernel IO subsystem. Kernel provide many services related to IO, such as scheduling, buffering, caching, spooling, device reservation, and other error handling. Okay, which provided by the kernel IO subsystem and built on the hardware and device driver infrastructure. So the IO subsystem is also responsible for protecting itself from errant processors and malicious user. So we learned about the CPU scheduling last time, right? Process scheduling, but this is more on the IO scheduling, because some IO request ordering via per device queue. They have some mechanism that they use for queuing, and then some OS also try a fairness between the process which request for the IO. Some implement quality of service, IPQS. This is for scheduling of IO. So other function for kernel IO subsystem is actually the buffering, which uh, responsible to store data in memory while transferring between the device. With this one, this buffering actually to cope with device speed mismatch. Sometimes when we transfer the data, the data transfer is lower speed compared to different memory to disk. Then we need a buffering to cope with the speed mismatch from different type of device. Also to cope with device transfer size mismatch. Maybe your flash drive or some other device, they only have limited block of size. They can transfer in 1 second, for example. Then buffering can help. That's why when you watch stream movie, you will use buffering as well actually. So, and then to maintain copy semantic, the information of the information of the OS itself. We can have a double buffering, which means the two copies of the data, either in kernel and the user mode, in the very different type of different size of data, or either full or being processed and not full are being used. Or you can use a copy on write mode in order to provide efficient buffering technique in some cases. Okay, this table, they call it device status table, actually manage the entry of each of devices, IO devices. Because when a kernel support asynchronous IO, for example, it must be able to keep track of many IO requests at the same time. Because if they support only synchronized, no issue, because only after complete the one task, then they continue with another task. But asynchronous, they can do a transfer in between, which the process still executed. So you need to keep track. So when you need to keep track, they need is stable. You can see the status. Is it idle, busy, idle or not? The idle one can be used, can be utilized, but the busy one is still waiting, only maybe for 1 or 2 requests only, cannot more. Okay, this figure is example of the device transfer rate, which will be used for the buffering. Okay, for example here, that a file is being received using via modem. We have modem here, 0.1 something, right? When you see here, this data from the modem, actually for the storage on the hard disk, you need to transfer to the disk. Then the modem is about 1,000 times slower than the hard disk. 1,000 times, okay. So the modem is about 1,000 times lower. So a buffer is created in main memory to accumulate the byte received from the modem. So the data from the modem will be transferred into the memory first. When the entire buffer of data has arrived, the buffer can be returned to the disk in single operation. So it means they didn't require to transfer time by time this slow, right? They collect everything and put in main memory first, then they transfer in one time only. Single operation. Since the disk write is not instantaneous and the modem still needs a place to store additional incoming data, so two buffers can be used. Okay. Then after the modem fill the first buffer, the disk write is requested. And then they will start to fill the second buffer and until there. That's why we call it double buffering techniques. Okay, because of these use cases. Another capability of the kernel subsystem actually catching. Catching is the faster device holding copy of data. It's look like our uh, hard disk also they have their catch. Okay. Always just a copy. That's mean not for permanent storage. Only for a copy. The key word is performance here. We need a best performance. So we're using this catch for faster device holding copy of data, so that they can work with faster operation compared to direct from the I/O itself to another I/O. Like the case of modem, very slow. They need an additional storage or additional device that can hold the data before make transfer to the disk. Sometimes also combined with buffering, depend on the system itself lah. And then we have spooling, which hold output for a device. If device can serve only one request at a time, the best example is printing, right? When you want to print, you click print your Word document, then the printer slowly grow, right? They have a certain time to start to print, and then at the same time you want to print many others, you just click print. So this is considered spooling. They hold the output of the device before it will be printed or will be executed. Normally they can put it in the main memory or sometime in the printer memory itself. Some printer, or especially for laser printer, they have their own main memory. Other than that, they have also device reservation function in kernel subsystem, which will provide exclusive access to a device which reserve, we call it reservation, right? Based on the system call for allocation and deallocation, and used for watch out for deadlock. If the deadlock happen, the reserve device can be used to avoid the deadlock. And OS that use protected memory can guard against many kind of hardware and application error, so that a complete system failure is not the usual result. We can minimize the occurrence of system failure. Only maybe a minor mechanical malfunction. So with the appropriate error handling, OS can recover from this read error, device unavailable, transient byte failure, and many more. So it can retry back, read or write, for example. Some systems may have more advanced capability in error handling, like a Solaris FMA, AIX, HPAIX, which can track error frequency. Means based on the log, they can track so that if this error frequently happen, they need to take some action. Stop using device with increasing frequency of retriable error. If they found that device caused many time of error, then they just disable it. This is more advanced features in Solaris and AIX. It will be very useful for servers to reduce the risk of failure. So most return an error number or code when IO request fail. They have the specific code. That's why when you having difficulty or failure of some device, they will put specific numbers of error. Normally the system error log whole problem report can view back what type of error, and then is caused by which IO, which process, and so on. So this error handling can be useful to avoid the system failure. We can give the option for the operating system to act for the error they face. Okay, I think this one enough for part 2. See you later in part 3 in IO. Okay, thank you.